Here, normalized resistance related to the reflection coefficient through this equation. Similarly, the normalized reactance related to the reflection coefficient through this equation. By rearranging the equation, resistance equation and this reactance equation, we can show that this is resistance and reflection coefficients are related through a circle equation. This rearranging this equation, we will be getting this equation. This equation is the equation of a circle with a center is r by r plus 1 comma 0 and radius is 1 by 1 plus r. Similarly, by rearranging this equation, we can show that reactance and reflection coefficient, a real term and the imaginary term related to the reactance through a circle equation. Again, here it has a center and a radius. Radius is a 1 by x and the center is 1 comma 1 by x. So here they are the circle equations. Circle equation, as we know, here circle equation has a center of h and k and radius is equal to r. So for a particular value of center h and k and radius r, as a value of y and x changes, we will be finding it follows a circle, it forms a circle like this. Keeping h as, for example, h is equal to 0 and k is equal to 0, center of the circle is 0 and radius is equal to r. As the value of x changes, y changes, so that forms a circle as shown in this figure. So here also for a fixed value of r, for h and k, here center of the circle. Similarly, here center is this value that depends upon the value of normalized resistance. So for a particular value of resistance that form a center and radius is 1 by 1 plus r. For this radius and this is a center, if you vary the value of real part of the reflection coefficient, that imaginary term that forms a circle as shown in these figures. For every value of resistance, there is a circle as similar to here. Every value of h comma k, we can have a different circles. They may take a circle position depends upon the center of the circle, that means the values of h and k. Similarly, here for every value of r, the center changes and the radius also changes. So for every value of r, there is a circle on the Smith chart like this. So here that imaginary part of the reflection coefficient and real part of the reflection coefficient. Is it like y and x of this circle? So and r is a normalized resistance. For each value of this r, there is a particular center and the radius. So that form a circle as shown in this figure. For example, r is equal to 0, we will be getting this circle. This is a circle, outermost circle is r is equal to 0. So as we can see from here, center is 0. This is a 0, center is 0 and radius is 1. Radius 1 is from here to here, the outer, from here this point to this point, that is the maximum, that is equal to 1. So that form a circle like this. This is r is equal to 0 circle. Similarly, as the value of r increases, center shifts towards the right side like this, towards the right. For example, r is equal to 0.2, normalized resistance is equal to 0.2, then the center shifted to some other point based on this value. Similarly, radius reduces here in this case, because r increases means this term will be reducing, radius reduces. So for r is equal to 2, we will be getting one more circle like this. Center changes and radius changes, the circle will be like this. So if you move over this circle, the value of resistance, normalized resistance remains the same. This is called as r is equal to 0.2 circle. So so like this, for every value of r, we can have a circle like this. We can draw a circle, and on the Smith chart, we will be having like this circles. And the value of resistance, normalized resistance, usually written on the upper part of this horizontal line. So like this is a 0.2 circle, 0.2 circle, and this is a 0.5 circle, and one circle. R is equal to 1. Normalized impedance R is equal to 1 circle here, and R is equal to 2. Like this, the radius of the one go on reduces as the value of R increases, and the shunt center shifts towards the right side. Finally, when R is equal to infinity, we will be getting radius is equal to 0, and center is coinciding to the rightmost of this chart. So this is looking like a point. So like that, we can have infinite number of circles for every value of R on the plot, or on the plot of this reflection coefficient of plot. So these circles are called as R circles, normalized resistance circles. These are called as resistance circles. So like this, we can have infinite number of circles, but it is difficult to show all circles over a Smith chart. On the Smith chart, only few circles used to be shown. See, it is like this. So these are called as R circles. R circles are like this. So this is forming a R circle. So center this on the Smith chart, as we can see here, there are many circles are there, and small values of small the gray circles also there. They are also resistance circles. So on the Smith chart, we will be observing that R circles are like this. These are the R circles. This and these are called as R circles. They are looking like this, and value of that circle is written over this horizontal line, so that we can see. So here this is a 0.4. This circle is R is equal to 0.4 circle, and if you move over this circle, the value of resistance remains the same. And similarly, this is R is equal to 0.3 circle, and this is 0.3 and this is 0.4. In between there are many R circles are there. This like this. There are four more circles are there. There those values we can read by from here to here. The variation of resistance is 0.1. So automatically each circle here, for example, if you take this circle, the value of resistance for this circle is 0.32. Similarly, this is 0.34. If the point is in between one more circle, we will be having like this. That is if that is 0.345. Like that, we can get a value of resistance for different circles. So here only few values are. So like here is R is equal to 1 circle is this. This is R is equal to 1. So resistance circle values, the value of each circle. This is the resistance circles. The resistance circles means its resistance has a particular value. That resistance value is written here on the above the horizontal line. So starting from 0.1, here 0 circle is this is the 0 circle. This last one is a 0 circle. Next is a 0.05 circle, 0.1, 0.02, 0.025, like this. There are circles are there over the Smith chart. They are called as resistance circles. Similarly, reactance circles also. Reactance circles. We can rearrange this equation that will form a circle equation here. So here reflection coefficient and reactance related to a circle. The circles are like this. If you draw the for a particular value of reactance, because reactance varies from minus infinity to plus infinity. For every value of reactance, there is a circle on the reflection coefficient plot or plane. Here this is the reflection coefficient plane. So for particular value of x, if you vary the 2r and 2i, that traces a circle like this. This is a circle like this. The circle like this. For example, if you take x is equal to plus 2 reactance value, and if you vary the 2r, we will be getting that they are 2r and 2i. They form a circle like this. This is a circle. They are forming a circle like this. So our this is a r is equal to 0 circle. This is the r is equal to 0 circle. Outermost circle is r is equal to 0 circle, and the value if you take a one more circle that goes behind r is equal to 0, that is the negative resistance. So on the Smith chart we have only r is equal to 0 circle, that is a last circle on the Smith chart. So here reactance circle, it will form a circle. If you take x is equal to 2, it will form a circle like this. Okay, but we are considering up to only this point like this. Outside of that we are not considering the value of reactance, the reactance value. So here similarly, if you take x is equal to plus 5, that will also form the circle like this. So reactance up to this point we will be considering. So they are looking like this. We're considering leaving this part of the reactance reactance value. So here, as we can observe, so for every value of x there is a circle like this. This is x is equal to 1 circle, x is equal to 0.5. So radius go on increases as the value of x reduces, and this is infinite radius here coinciding with this horizontal line, that is x is equal to 0 circle is coinciding here. And so if you take a negative value of reactance, the circles will be forming like this. This is a circle associated with the x is equal to minus 0.5, and x is equal to minus x is equal to minus 5, x is equal to minus 2. These are the circles, they form circle like this. Okay, so these circles, they are also these are all reactance circles. If you complete them, they will be forming a circle, but we are taking the reactance only up to this r is equal to 0 circle. So this these are the circles with reactance values negative, and upper part of this chart the circle values are positive, and below are negative circles, negative reactance circles. So like that in on the Smith chart there are circles are there, reactance circles are there, like this. So if you move over this circle, the value of reactance remains the same, that is equal to 1. Similarly, if you move over this, reactance value is equal to 0.5. Okay, so like that there are reactance circles are there, positive circles are in the reactance circles are in the upper part, and negative reactance circles are in the lower part. If you move over any of this reactance circle, reactance value remains the same, like a minus 0.5. If you move any point from here over this, it is equal to minus 0.5. So like that reactance related to the reflection coefficient through a circle equation. Every value of x there is a circle over a Smith chart, but again it is impossible to show all reactance circles over the Smith chart. On the Smith chart we will be having only a few circles, see like this. So this is a reactance circle here, this is reactance circles like this. So the reactance circle values are written here, the value of reactance are written outside the circle. So this is a reactance value plus 5. So the value of reactance is written outside the circle. Similarly, we can see here reactance written, that is plus 2 reactance value, it is written outside that circle, plus 0.2. They are on the periphery of this r is equal to 0 circle. You can see these are reactance values. Reactance, this circle, its reactance of this circle is plus 0.5. Similarly here plus 0.2. If you go to this circle, its reactance value is minus 1. So like the reactants are written on the outside of this circle. These values are the reactance values. We can see here it is written here is 1.2, reactance value is 1.2, this is 1 and 1.4. So if you move like this over this circle, the reactance remains the same. Similarly here, if you take this circle, this is a 5, reactance value is equal to plus 5. If you move like this, that value, reactance value remains the same from here like this. Okay, so similarly here below also the reactance values are minus 1, but it is not shown minus, but the value of reactance here is a minus. For example, if you take this circle, this is a circle, reactance circle, its value is equal to minus 1.4. So if you move over like this, from here like this, if you move, the reactance value is equal to 1.2. Similarly, like for all the values below or whatever the circles are there, reactance values are negative. Similarly, above are positive values. So these circles, this circle and this, they are the reactance circles, and these are the resistance circles. So this, in this plot, resistance and reactance circles are shown overlapping. On the same chart, resistance and reactance circles are shown on the, this is a resistance circle and reactance circles. If you combine those two, it will be looking like this. So reactance circles are, these are the reactance circles, and these are the resistance circles. Overlapping of reactance circles and resistance circles, this is called as a impedance chart, Z chart. Okay, so and in this Z chart, we can mark the impedance. The impedance means here reactance circles and a resistance circle. They are the normalized reactance and normalized resistance. So if you know the load resistance, if you know the load impedance, like for example, load is equal to, so this is a circuit here, load ZL is connected to the transmission line, it has a characteristic impedance Z0, and ZL is equal to 100 plus J50, and Z0 is equal to 50 ohm. You get a normalized impedance like this. This is a normalized impedance 2 plus J1. This we can mark over the Smith chart. So that is this is a point. To mark this normalized impedance over the Smith chart, we should take R is equal to 2 circle and X is equal to 1 circle. So R is equal to 2 circle, we can find the R is equal to 2 circle by looking at the value over this above this horizontal line. So numbers are there here, 0.2, 0.51 like this. So this is equal to, this is a 2 is written, so that is R is equal to 2 circle. This is the R is equal to 2 circle. And next X is equal to 1. So we have to take X value. X value, if you see here, X is equal to 1 here. So we have to take this circle. Intersection of these two, X is equal to 1 circle and R is equal to 2 circle. That is this point. Intersection of X is equal to 1 circle and R is equal to 2 circle gives the normalized impedance. So we can mark this over the Smith chart like this. So any impedance we can mark like this over the Smith chart by taking a normalizer, because the Smith chart is normalized chart, as we saw in the reflection coefficient related to the normalized impedance. So we have a normalized chart, so that is a reflection. See, so that you can see here on the actual Smith chart, the one available like this. Okay, R is equal to 2. R is equal to 2 means this is R is equal to 2. So this point is R is equal to 2 circle. So we have to move over this R is equal to 2 circle. This is R is equal to 2 circle like this, and X is equal to 1 circle is this. X is equal to 1. X is equal to 1. So we have to move over this circle, and you see wherever it intersect with the R is equal to 2 circle. So this is equal, R is equal to 2 circle, and this is X is equal to 1 circle. They are intersecting here. So we have to mark the point here, impedance point at this position. So we can mark like this impedance over the Smith chart. Similarly, this point, this is here R is equal to, we can see the impedance at this position we can read. So this is the intersection of this reactance circle. So reactance value we can read here. This is a reactance value. So this reactance is a 0.4. So 0.4 circle is passing through this, and resistance circle we should move like this. So if you come here, it is in between 0.3 and 0.4. So at somewhere here. So the approximate value of the resistance is 0.35. So it is a 0.35 is a resistance value, and reactance is a 0.4. So at this position, the impedance value is 0.35 plus zero point 0.4. So like that we can get a impedance value at any position by reading the value of reactance passing through that point and the resistance value passing through that point. So this is about a impedance chart. So it is a overlapping of two circles, resistance circles and reactance circles. Overlapping of those two gives rise to the impedance chart. Impedance chart. The values of reactances are written outside the circles, and the periphery of this outermost circle, they are written. See, these are the reactance values, and resistance values are written here. So while reading, we have to read the values here. Reactance values are written here, and resistance values we have to read from here to get the value of any impedance. So on the Smith chart, we will be having these two circles, resistance circles and reactance circles. They will be looking like this.